Hi and welcome to this video about process snapshotting. It's what all this is about. Well, what happens inside the process? We know that processes are management objects that have multiple resources within them. For example, we have memory blocks that are being allocated by various components in the process. We have map files, we have images, that is DLLs. Various DLLs map into the address space of the process. We have handles to various kernel objects. We have threads, of course, that actually do the work and execute code. We know that every process has at least one thread that is created initially, but then more threads can be created. So how can we see what's inside the process? So obviously we have many tools at our disposal. We have tools like a Process Explorer from sysinternals to see what's going on in a process in a sense of threads, DLLs, things like that. We can use other tools like VMMap to see what memory regions are being used in the process. And so we have these various tools out there. But what happens if I want to do something myself? I want to look at the process from a programmatic way. And so how can we get that kind of information if I want to build a tool that looks at a particular process of interest, or maybe multiple processes, maybe even comparing the state of processes or the same process in different points in time? So the GUI-based tools are very nice, but they're not as flexible as you might need for certain kind of work. So how can we get that kind of information? So obviously, if you've done any kind of work on Windows, you know there are APIs. For example, the standard Windows API has functions such as create tool help 32 snapshot that can provide a list of all the threads in the system, and then if you filter that by the process ID you're looking for, you can get information about threads. Well, at least you can get some information about these threads, but it's not a very deep one. You get things like the thread ID and well, not really much else. If you want to go deeper, you might need to use other APIs which are not officially documented. Another example is Query VirtualQueryEx, which is a documented API to allow us to enumerate all the memory blocks in a process. So we can definitely use those APIs. And if you want more details that we can't get with the standard Windows API, we can go to the native API, which you can find more information in my book, Windows Native API Programming, but also in my courses and in fact in some of the videos in my YouTube channel. So for example, ND query system information can enumerate all processes and threads across the system and give you much deeper detail into all the processes and threads, but you might get even more information that you actually need. If you want to focus on a single process, you'll have to filter out lots of details which you just don't need. You can get information about memory and handles with other APIs, but again, you sometimes get more information that you actually want, and you'll have to filter these things out. And in general, this requires multiple calls. And of course, you have to save that in some form and then go over the information. This is quite a hassle, especially if you want to get multiple levels of detail in the process. It requires multiple calls, which means it is more costly. You have to do the transition from user mode to kernel mode for every one of these APIs that you might need to call multiple times. For example, Query VirtualQueryEx gives you the one block from a particular address, but then you have to call that another time to get the information about the next block that you know its starting address, but you don't know how big it is. And so you have a loop calling these APIs, which again go to the kernel. So this is fairly complex, expensive, and sometimes really more than you need. So is there another option? So fortunately there is. And this is called process snapshotting. Process snapshotting is a feature that was introduced in Windows 8.1 and Server 2012. And so what it allows you to do is to take a snapshot, like a picture of a process with various elements in it, and you can choose what elements you'd like to capture, and then you can analyze that snapshot. And the capturing is done using a single API. So all the actual tracing of information, getting all the details is done directly by the kernel. So it's much more efficient than calling from user mode with multiple APIs and then just filtering things out. And so the basic API is the function PssCreateSnapshot. You call this function with the handle to the process, as I'll demonstrate, that you'd like to look into. And you need to provide a set of flags indicating what kind of details you'd like to have for the process. You don't have to capture everything. You can capture just a subset of interest. And then you can start looking at the snapshot by using some helper APIs, PssQuerySnapshot for single instance things like the general process information, for example, memory blocks, things like that. Is just kind of the one thing that you can get. But if you have something that is in multiple data, multiple elements like list of threads and handles, things like that, then you have another API to do the walking over the snapshot, so to speak. It's called PssWalkSnapshot. So I want to demonstrate both of these, or all these APIs that you see here, to give you a sense what that looks like when writing code. So just again, is to recap, if I have a tool like Process Explorer, I can definitely look at the lower pane and see information about threads. There's quite a bit of information here about threads in this particular process. I've just put my selection on, in this case PowerPoint, and I can go and see information about DLLs loaded into the process address space with some considerable number of details. And I can also get the handles of all the objects that are available to this process at this point in time. Just note that by default we only get the handles to objects that are named. If you also want to see something about an unnamed object, you need to go to the view menu and select show unnamed handles and mapping, something I described in an earlier video in this YouTube channel about Process Explorer in general. So we can get all that, and again, there's no good way to take a snapshot here unless we take a dump. We can technically right click and try to create a dump file here and then try to compare these dumps if you find a tool that can do that for you. So a dump is definitely an option, but maybe a bit more than you actually need. So this is where process snapshotting can really help. So let me go ahead and do an example of that. So first, just for fun, this week Visual Studio 2026 Insiders, which is like the old previews, has been released. I'm going to use that. It has a slightly different UI, so let's go ahead and use that by creating a new project. That's Visual Studio 2026. Let's create a console application as always. So again, I have to do some filtering here. I've never created a new project in Visual Studio 2026. So here goes the C++ console application. And let's call that Snap. I think that sounds good. So we have here YouTube code. Let's put it here. So and create. So we'll see if everything works as planned, even in this newest addition to Visual Studio. So I have a little tweak I have to do here in terms of one tool that I've installed. The options also, there's new options. So just maybe an example that I can just demonstrate here. So in this case, I'm looking for an extension called Tweaks, which I like, but some of its default settings I don't like, which is the thing that I can't change the zoom with the mouse. It prevents that, but I actually like it. So I'm going to change this. For now I can, well, after I reopen the file, I can now change the zoom for the font, which is something that I typically do for demonstration purposes. So let's go ahead and start as usual with windows.h and stdio for our trusty printf kind of thing. And then we can go ahead and begin our snapshotting. So as usual, we want to snapshot a certain process. So to make things a bit easier to check or to select, we're just going to grab the process ID out of the command line. So if we don't have enough parameters, we'll just say that the usage for this thing is snap with the process ID. Now, technically, with a more elaborate example, I probably would also allow different things to be captured to provide that ability on the command line, but I'm going to leave that for the interested viewer because I don't want this video to be way too long. And it's not that interesting. I'm just going to choose a certain set of flags to use. So now we need the process ID, so let's go ahead and grab it by using something like string to unsigned long. We'll grab the first parameter on the command line, We don't care where this thing ends, and we're going to use 0 for the radix. That's the base of the conversion, which means it also allows us to get something like an hexadecimal value with 0x as a prefix. That's kind of a nice thing str2 thing allows us to do, which is much more powerful than the A to I or these kinds of APIs from long ago. So once we have a process ID, we need to open a handle to the process. Now, if you look at the documentation for the PssCaptureSnapshot, the thing that we're going to use, there's no indication what kind of access mask we need. And that's because the access mask depends on the flags we're going to use, indicating what kind of data we'd like to capture in the process. And so we can try to be as precise as possible here if we know what we're looking for and we know what to specify. But I think the simplest thing to do here is to use the maximum allowed constant, which basically says, give me the most powerful handle I can get for this process. That's the simplest thing we can do. So we'll get something, and if it doesn't work out for what we want to capture, then tough luck, we'll just have to give up in this little example. So I'm going to provide a process ID. So if this fails, we get a null process ID. There's really nothing we can do. Well, technically we could perhaps, well, actually we can't do anything in this case. And that would be the case for example, protected processes that we might not be able to open in a very powerful way. Even if we can get process query limited information, that's probably not going to help us a lot with process snapshotting. Anyway, we can fail for other reasons, like process ID being a junk PID that doesn't really exist. So we can just say error. In fact, I'm not going to bother with error handling here to save time. Just return 1 and forget about it. So once we have a handle, then we can move to the next step, which is the capturing of the snapshot. So here's where we can use the function PssCaptureSnapshot. Now it's not really defined here because we have to add another header for that. It's in a separate header. It's called process snapshot something. So here goes, process snapshot. Seems to be like a good enough name. And now we can use PssCaptureSnapshot to use this. So the first thing, of course, is the process we'd like to capture information for. And then we have a long list of flags. All start with PSS capture something. You can see there's various things we can specify here, like handles, and then we can specify other things like threads. And again, there's a long list, and of course it's mostly documented. We can press F12 to see all these values right here. You can see that even if I say handles, that's actually not perhaps enough, because handles only provides handle numbers. What I'd like is more information, like name information and basic information. So basically it's about just taking in all the flags that I think that I need. So here's name information for the names of the objects that I have handles for, if they have such a name. And you can see for threads, we can even get the thread context. So we can see where that thread is in terms of where it is in the code and the values of registers. We can do even that. We can also capture the virtual address space, things like that, including section information, meaning information about mapped files. So I can grab a few more of those just for fun. Not going to show everything because there's just not enough time for that, but you can try these things yourself, of course. In fact, there's also a nice interesting flag called VA clone, which allows you to, which basically creates a clone process. That's another process that has the same mapping for memory, and this is what you're actually looking at. You're looking at that clone. So a very interesting thing to see. Well, it's not that easy to see, but it is definitely possible because it's not going to show up normally on Task Manager, but it is something we'll be able to see if we look deep enough. So there are a few more things here. I'm not going to use them. I think that's enough. Next, what we need is just the result, really. So actually the snapshot itself is returned via another parameter. So let's use the definition here for that, and what we get here is an error, basically. So if we get something here that is not 0, which is technically the good way to write it is like so, with error success. So if it's not error success, And then obviously something went wrong. We couldn't get the snapshot for that, the things that we asked for, and that's something that definitely can happen. Let me see what's going on here. HPSS, I think I'm good here. So we have thread context flag. Sorry, missed that. So with thread context flag is really about what kind of information I'd like to get if I ask for a context for a thread. So if you're familiar with the context structure, there's a flag there indicating how much detail you'd like to get for the context. Like, do you want to have just the instruction pointer, or maybe you want to see all the registers at the time, and so on. Since I haven't asked here for a thread context, just to simplify things a little bit, I can specify 0, and that would be it. So if we get an error success here, everything is fine. If not, and something went wrong, we can just exit. Again, I'm not going to do any error handling here to save time. Once we have that, we can start walking over the information that we got. So we have the snapshot, and now we can display information. So for example, we can do something like display processing for like some information which is always available. We don't have to ask for it. So here's the display process info. Let's go ahead and use display thread info to display some information about threads. Again, passing the snapshots. That snapshot handle is the thing that you can pass around that represents the actual snapshot. All the other APIs will use that parameter to get to the information. And we can go ahead and continue with the same idea with other things like handles info and so on. Of course, if I didn't capture something, obviously it's not going to work out. Once we're done, we don't need the snapshot anymore. We can go ahead and destroy the snapshot. Basically deleting that snapshot. So it's a free snapshot, whatever that name is. So we have free here. Of course, it doesn't matter once we exit the process, then the snapshot will be destroyed anyway. But just to be kind of nice and work correctly, we're going to destroy the snapshot and then just close the handle to the process. So that's what we're going to do. So let's go ahead and try to fill in the blanks with these functions here, like display process info. So here's the function. Let's go ahead and we have here the snapshot. So process information, the singleton thing is just a single instance of that. So there's no walking over multiple items, just a single item there. In this case, the function is PssQuerySnapshot. So this is about querying singleton things. We have to provide the snapshot, of course, and then we have the PssQueryInformation class indicating what kind of information we'd like. So we can see PssQuery, we have lots of details we can get there depending on what we're looking for. And right now, we want the process information. So we have PssQuery process information, that's the thing we want in this particular function. And then we have a buffer pointer we have to provide and the length. And of course, based on the type of information, we have the appropriate structure, which is of course documented, that we have to provide. So this one is called PSS process information. So it's pretty straightforward and at least consistent in terms of naming. So in this case, if I look at PSS process information, I can see that the information here is fixed in size. So there's nothing here which is variable in size. We have values or pointers, but they don't point to anything that's being written. And even the image file name has a fixed length here, which means it's easy in terms of size. We know what the size that we need. The size is exactly size of info. So if we have that, of course, we have to check that. Technically, we have to check that, although with the snapshot for getting process information is always going to succeed. Still, I'm going to just check to make sure. So if we have that, we know that the information is there. It's just a matter of displaying information. So I'm going to just do a few of those, not to drag the video for too long. So let's say the image file, for example, that is the executable file. We have that in the info.image file name. Okay, so that's one thing. Of course, we have the PID. That's not a big secret. We actually knew the PID because we've got it from the command line. But still, let's just display that for the process ID. Notice there's also the parent process ID. So that's good. Let's just grab that as well real quick because it's just there. And we can do some copy pasting here. So that's the parent of the process that we're looking at. And there's some other stuff here. For example, we can see there's an exit status if the process had terminated. In this case, probably not going to be the case. There's also create time, the time the process was created, kernel time and user time, that is time the process has executed code in user mode and kernel mode, basically combining or accumulating all the threads in the process. The address of the PEB, the process environment block, and other details like the priority class and so on. So there are APIs to get most of that information, but here we get everything that we can probably going to need in one nice stroke. Okay, so that's good. That's one thing, some information about the process. We can start with that. And then let's fill in something that are a bit more interesting, such as the case of handles. So, or maybe threads. So we'll see what we want to start with. But in any case, there's some basic information, and then there's some more specific one for each item, that is for each thread or for each handle. So let's do something like display handles info. And again, we have our snapshot here. So what are we going to do here for working with handles as an example? So first we have some details which are generic in terms of all the handles in the process, in terms of some statistics. So you can do something very similar to what we've seen here, but using a different structure. In this case, that would be handle information. So we have handle information for information about all the handles in the process in general, and then we can start going over each handle and seeing what's going on with that. So we have query something like handle information. So I'm going to use that to get information about handles. So if that works, we can get something. Let's see what we have here. So in info, we can see there's very little information here, just the number of handles. Well, we have to start somewhere. Of course, it's more interesting to see what is each handle pointing to, but at least we know how many of those handles there are. So once we have that, we can now start doing the walking, in this case, over all the handles. And the same idea applies to threads and to memory blocks. It looks really, really similar. So the idea here is to start with doing a walking kind of thing. And this is done using the function PssWalkSnapshot. And so we have PssWalkSnapshot that requires the snapshot itself, that's for sure. And then what kind of walk are we going to do? So I'm going to do PssWalkHandles here. That's what we want to do in this case. And then we have something called the walk marker handle. So what is that? The idea here is that since we have to walk over items, there should be some kind of internal pointer maintaining the location or the position where the current item is. And the way this is abstracted with the API is using this idea of a walk marker. So we need to create this marker and pass it along, and every time we pass it and get some details about a particular object, it automatically advances to the next item. So what that means, it means we have to create this marker. So we have PssWalk marker create. We have to create that once. And there are two parameters here. The first one is just a way to customize allocations done internally by these APIs, which we don't care about. So we can specify null and use the default allocator provided by the API. It's an advanced thing, which is not of our interest here. And then we have the HPSSWalk handle as a result. So let's call that HWalk and get it here. So we're creating an initial handle for that walking thing, and of course technically this also could fail, so let's go ahead and just check that. So once we have this handle, now we can technically use it. It will automatically advance to the next location. So we have HWalk here, that's the walking handle, and then we need to provide the appropriate buffer, which is based on what we are trying to capture. So in the case of handles, again, it's all documented. There's a structure called PssHandleEntry. That's what we want, so let's call that entry. And so we're going to use entry here. and the size is going to be size of entry. We'll see if that actually is a good thing to do, but we can start with that. So this technically is the way to walk over items. Now, whether we succeed or not, we have to check that, because at some point we get an error that indicates that there are no more items. There's a special constant called the error no more items, indicating that it's not really an error, just indicating that we're done. So there are no more, in this case, handles to describe. But as long as this function continues to return error success, we can definitely know that there's something valid in this structure. And again, we can look at the structure here, or in the documentation, you can see there's some interesting stuff here. There's some generic things like the handle value and some flags, the object type this handle represents. There's a bunch of object types that are being tracked or captured by these APIs. Not all object types, by the way, only I would say the most common ones. We have the handle count and pointer count and other details which are not that important. Creation time is also something you won't actually find for most objects, even though it sounds like a nice thing to have. And then there's also the object a name, if it has one. You can find it here. You can see it says valid for the lifetime of the walk marker, which means it's okay to read this thing, but we can't just keep the pointer. If you want to use that later, we have to copy the string that is pointed to by that if you want to use it later, because then once the marker moves forward, then this information is going to get lost. And then for specific types of objects, that is specific types of handles pointing to these objects, we get some extra details. So if we have a handle to a process, we get some more information about the process this handle is pointing to. If it's a handle to a thread, more details about that thread. If it's a handle to a mutex, more information about that, like the owner of the mutex. Again, to get that information a different way requires a native API, another call, and something which is not truly documented. All this stuff here is fully documented. You can see there are other objects here like events, sections, and semaphores, which I can say are definitely the most common objects to be used in Windows programs. So just like before, we can grab some details and display them just for fun. So I'm going to just display something so we can see something. So we have the handle itself. So here's the handle itself, that's the actual handle value in the process. The same information we typically see in Process Explorer. So we can perhaps do some casting here for the compiler to be happy, but it's not really important, it's just a number at the end of the day. Now, what about object name? So object name could be interesting. So we can say that if the entry, we have the object name length. So if this is greater than 0, which means there is an object name, then let's display the name as well. Let's do a little space here. You know what, let's remove the \n here and display the name. So the name is going to be Unicode string, and then we'll add a \n later on. And so the name, notice here, might not be actually null terminated. There's no requirement for that. That's why we have the length here. So this is slightly tricky, although it might be that it is null terminated as it happens to be null terminated, but there's no guarantee based on this API. So we need to be careful here. So I'm going to use a string here. I'm going to start with the name, the object name, and then I'm not going to take everything. I'm going to take based on the object name length. And since this is provided in bytes, I have to divide by size of white character, which is just 2, to make that in characters, because that's how the W string or the string constructor requires it in this case. And then I'm going to do CSTR for printf to work correctly, because it's not really supporting strings directly. So it's just manipulations which are not super important for our purposes, but just for correctness. So we have to add another include here for string, so the compiler is happy. This is the C++ standard string function here. And that's it. We can continue doing that in a loop. We can, of course, add more details. As you can see, there's lots of details there. It's just so many of them. I'm just showing a few of them to save time, but for the interested viewer, please add more details. And if you're really interested to dig even deeper, then see if you can create snapshots every so and so often. See if you can compare them in any meaningful way and see, for example, new threads haven't been created, handles being created or destroyed, and maybe even create a graphical tool to visualize all this information that could be very interesting in practice, depending of course on what you're trying to do. So I'm going to remove this thread info here. I'm not going to implement that. You get the idea. It's very similar, but the video is becoming too long. It's time to at least try to test it. Of course, there's a few more things we have to do, like to be nice, to do some cleanup, like a PSS walk marker free. We need to free that, but again, I'm going to not do that here to save time. It's not too bad for this kind of application. So let's go ahead and see if we can actually do something with that. We have some warning here because the handle with %u, this one is not very happy. We need to do another cast here for the compiler to be happy, but it doesn't matter, it's just a number, so that should be fine. And then going back to Process Explorer, let's choose something to work with, and PowerPoint seems like a good idea. It certainly has handles with names and all that. It's pretty interesting process. So it's a 56580. Okay, good. So let's just go ahead and open a command window and go to the appropriate location. So we have dev YouTube code, and then we have snap x64 debug. Okay, so we have our snap application here, and already forgot the process ID. So we have 56580. Let's see if that works. Okay, so that definitely works, but I've forgotten the \n, and this is what happens in these nasty cases. So everything is the same line. Let's have a \n here to make it easier to see. Let's give it another shot. So now it's better. So we can see that there's lots of handles in this process, which is of course something we expect. Before the handles are starting, we should see some details about the process. Indeed, we see the image name here, the process ID, the parent process ID. We can verify by double-clicking PowerPoint in Process Explorer just for fun. And you can see that the parent ID here is 13276, which is an Explorer process, which makes sense. So you can see the process ID of the parent is indeed correct. And there are 5,705 handles in this process. And we list all of them, including those that have names, but also including those that don't have names. This is just a matter of choice. We could have just filtered out and just shown all those that have names. So you can see lots of handles here, including handles to registry objects, where we don't get some extra details, but that's like enough. Once you know the name of the key that's being opened here, that's enough information. There's really nothing else you're interested in the case of that handle. So we can definitely play around with that and remove some of the information, maybe just taking and doing that. So basically saying that we're not interested in handles to objects that don't have names. And that would be like easier on the eyes perhaps. So here goes. Anyway, that's process snapshotting. It's pretty powerful and very easy to use. Also, by the way, there's a flag you can specify where we get statistics about the mechanism itself. How long does it take to take a snapshot? How much memory the snapshot itself takes? And I didn't have time to show you the clone process. That's maybe something I'll do in a different video. So that's process snapshotting for you.